Today we have Nalin presenting on Nova and his work on Nova Scotia. So yeah, thanks a lot for coming, Nalin. Yeah, the floor is yours.
Oh, perfect. Yeah, so I guess I'll just talk about Nova and some of related work with Nova Scotia, and then Lurk language, which has been pretty cool. And a lot of this work is, by I guess Microsoft and Srinath from Microsoft. And Lurk is by Filecoin. So I guess Nova Scotia is just like some open source project that I've been helping out with, and a couple other people. Um, yeah. So I guess first to get started, I should be clear that there's many Novas. So this is not Arbitrum Nova, which is some data availability committee thing. And this is also not Tornado Cache Nova, but it is closer to Tornado Cache Nova. It is Microsoft Nova, which is a proving system kind of setup. And I guess Justin Drake and a few other people actually think of this as like more of a preprocessor than a proving system. So that kind of framing is useful to keep in mind. And hopefully, as you go through the talk, it will make more sense why that is sort of the right way to think about this. Right. So yeah. Oh yeah. I guess feel free to just like interrupt me or ask any questions or anything. I've not really given this like talk before or anything, so it is probably helpful for me to you just like interrupt and ask questions. um, okay. Let's see. Right. So to get started, I think Nova is like I just to motivate like how Nova is constructed. It's like quite elegant and like pretty straightforward how you would do if you just like sort of have all the pieces in mind. So to get started, I think let's just start with like motivation, right? So one very common, or I guess one thing a lot of people have usually seen is this like setup of Starks um in SNARKs. And I guess particularly the setting that most commonly with this kind of setup you've seen is like zkVMs, and Polygon, for instance, has I think all of their teams have converged on this setup where essentially as the state machine proof, they create a Stark proof, and then take the Stark proof, which is slow to verify, and then verify this slow to verify thing in a SNARK proof of like Blanc or Grad 16. So really what is going on there is like, you want a proving system that, or at least like your whole stack, you wanted to have two properties. One is, you wanted to have a fast prover, and then also you wanted to have a fast verifier. So the Starks have a fast prover property, but unfortunately Starks don't have a fast verifier property. And Plonk or Grad 16 have the fast verifier properties, but they don't have the fast prover properties of state machines that zkVMs would need. So Nova is the observation that for the fast prover setting, in case of Starks, for instance, you're doing a lot of things, right? So for, I guess not to go too much into detail, but the way Starks, you create like some air itemization, right? You compile it down to like some poly IOPs, and then for these poly IOPs, you run some fry protocol or like deep fry or whatever, right? To actually verify that these work, and then you have a bunch of optimizations and whatnot. I guess it's like the sort of story is that you're going through this heavy machinery, right? Of taking like some relationships, converting them to some polynomial IOPs, then verifying that polynomial IOPs with like some cryptographic compiler. And Nova, I guess, is sort of the observation that instead of going through all of this machinery, what if we just like delete all of this, and instead just within this like arithmetization land, in the case of Nova, this arithmetization is R1CS, can we do recursion, right? So we take as input some R1CS constraint and I guess some witness, right? And we want to be able to recursively verify many instances of this. So in case of Starks, you would be doing all of this heavy machinery, but with Nova, the sort of clean setup, you have this only R1CS setup. Right. So yeah, so Nova is essentially this construction which figures out how to do this. So let's say transforms. Let's say 2 R1CS into 1 R1CS. So in reality, this is not R1CS, and we'll see that this is like some relaxed R1CS, but that is still sort of the key idea. So right. So so let's see, how do we okay, so Nova. Right. So Nova is I guess one really good way I think a lot of people motivate is like Nova arises from homomorphic commitments. Let me see, homomorphic commitments. And homomorphic commitments, I think the most common example is sort of BLS signatures, I think, is one common example. So in the case of BLS signatures, you have this setup where you're able to, so to verify one signature, you're verifying some pairing that is something like, E of the public key and the signature, or actually it's the other way around. It's like hash of the message and the public key is equal to E of some signature and generator or something. And it turns out that, actually, I'm not sure if this is the exact equation, but just the general idea is just like, you're able to add public keys as well as add signatures. And you saw if the additive thing verifies, then you're confident that the sort of the inputs to the additive thing were also correct. And this works because multiplication retains this homomorphic or linearly homomorphic property. And it's, I guess it's the case is that let's say you have 2 public keys, then multiplying these by some value, let's say R, gives you R times this plus R times this. And this is also still true if you do this on the pairing setup. So I guess the key sort of takeaway there is that in the case of BLS signatures or any linearly homomorphic scheme, you're able to take multiple instances of the same kind of thing and aggregate them into one. And this is very much like recursion, right? So if you could do this exact same thing, but instead of verifying signatures, we would be verifying, let's say, constraints in NP, right? Or R1CS or anything of that sort, then we would be done basically, right? So essentially, what we need is some way to do homomorphic commitments, but for R1CS in specific. So so for starters, let's start with some toy example of how you might try to construct this kind of scheme. And the paper or I guess the Nova paper in section 4 goes into a lot of detail about this. I don't have it up here, but I guess the short story there is like they start with some example that doesn't work, and then they show how to modify and motivate exactly why you need the relaxed R1CS. And then things start working nicely. So let's kind of do the same exercise here. Let's start with the toy example, and a good toy example is like something very simple, right? You have, let's say, some vector A, and you dot product it with some witness, let's say Z, right? And Z, right? And let's say you also additionally know that this is 0. And this is, I guess, the sort of relationship you're trying to verify. So almost exactly like, the BLS example, this is, like you can almost think of this like, oh, I have a signature, which in this case could be, in this case could be Z, right? And then I have some public key, which is A, and then I get some output that my pairing would need to verify. Right, so analogously, we have some similar relationship, but in fact, we'll see that this is much simpler. right? So let's say, we have two instances of this kind of thing. So we have a dot z1, which evaluates to, 0. Let's just say big 0. And then we have a dot z2 also evaluates to 0. Then one very cool trick that people generally in SNARK will use. In fact, I think the first time I saw it was in some scroll ZK EVM circuit. Is this trick of RLC. So that stands for random linear combination. And the way random linear combination, I guess intuitively works. It's like if you have some, so there's this lemma called Schwarz-Zippel lemma, which says that if you have any, I guess, polynomial relationship, it has, order degree zeros, or it only evaluates to some exact value at a very few points. So if you have a very large field, the probability that if you randomly sample a point and some relationship holds true, you can believe that that relationship holds true over the entire field. So how can we use that here? So, let's say we create some, Z3, right? So we had earlier two, I guess, relationships, right? A dot Z1 is equal to something, and A dot Z2 is equal to something. Z1 and Z2 are separate, A is the same. So now let's create some Z3, right? And let's say Z3 is equal to Z1 plus R times Z2. So here you have the R, and this R is sampled randomly. So what does that mean? So in practice, if you would to implement this, you would do like some Fiat-Shamir thing. And Fiat-Shamir just says that, let's say I put Z1 and Z2 as fixed values, input them into some hash function, and this hash function is, secure and whatever. And then in that case, no one should be able to predict the randomness R. Right. And now with this randomly sampled R, I have Z3 equals Z1 plus R times Z2. Well, I guess what happens when you plug in A dot Z3, this is equal to, A dot Z1 plus R Z2, which, is still 0. Right? It's just like, 0, 0, 0, 0, whatever, plus R times 0, which is still 0. Right. So if I only verify this third relationship, then A dot Z3 is equal to 0, and then I have some way to check that Z3 is equal to Z1 plus random times R2 or random times Z2, then I'm confident that in fact A dot Z1 is equal to 0 and A dot Z2 is equal to 0. Right. So what did we have to do here? Let me just make a quick note. We had to check that A dot Z3 is equal to 0, and then we had to check that Z3 is equal to Z1 plus R dot Z2. So we had these two checks, and with these two checks, it's sufficient to combine these two separate relationships into one. And in fact, you can do this for more than two, right? If you had many, 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 you would have something like A dot Zn is equal to 0, and then check that Zi is equal to Zi minus 1 plus, or yeah, Zi minus 2, or something of that sort, right? So you would have n of these checks and one of these check, right? One check, n checks. So let's say we wanted to do this as sort of one of the I guess this is just like the equation we want to check in recursion or something, right? Then one thing you can do is like in your like recursion circuit, you verify each step that this Zi equals Zi minus 1 plus R times Zi minus 2 equation holds. And then at the end, you just do this A dot Zn is equal to 0 check. And this is pretty similar to how Halo or I think some of the Blanc schemes also do split accumulation. And essentially the key idea is that we can break down the main check into two parts. One part is like the heavy part, which in this case, is the a.zn equals 0 part. And then the rest of the n checks we can just do within the circuit of like recursion. Right. So this was just like the toy example. And now let's actually do some R1CS, right? So what does R1CS look like? Oh, I guess one quick note is that R1CS is like rank 1 constraint system language, or I don't know, like expression, right? And the cool part about R1CS is that anything in NP can be converted to an R1CS instance. And so it is like, an expressive enough language that, not just some a.zn equals 0 relationship, but any relationship at all can be verified using R1CS. And roughly R1CS is just like, the ability to do additions and multiplications. And in practice, I won't go into too much detail about how R1CS looks like, but essentially R1CS gives some output that's like a.z equal b.c equals cz. And this dot is actually, I believe they call it Hadamard product, right? Or essentially elementalized product. So essentially you have some relationship of this sort that instead of the toy example relationship we had, we want to check. So same way as the toy example, let's say we have two instances of this. Right. And we want to do the same kind of RLC based aggregation. So RLC, let's say Z3 is equal to Z1 plus RZ2. And so now if you try to plug in Z3 into this whole thing, it actually turns out that this equation is not true, because so what is happening here is that you have something like this. Okay, Z1 plus RZ2, C1 plus RZ2. And then you can imagine when you open these brackets, what actually ends up happening is that this AZ1 term gets multiplied by it's like element-wise product. So any term of this sort gets multiplied once with this, and then once with this and this. And then same on this side, you have something like, so when you open it, it expands into more terms. And the way it exactly expands is that there is some term which is like, Z1. So there's some, let's just leave this blank for now. There's some term that's like, Z1 square. There's another term that's like Z2 square. And then, there's a third term that's like Z1, Z2 or something. Plus another value that's Z1, Z2. Something of this sort, right? And essentially the observation of NOVA is that to create a folding scheme for R1CS, what we can do is, we can give these two terms also some variables, D and E, let's say, right? And instead of making our original equation be this, we can make the original equation be something like D plus DZ plus EZ, I believe. So I guess these Z's are not exactly, or let me just make a distinction here. Z dash, right? So instead of actually verifying the original R1CS equation, we will actually work with this relaxed R1CS form. And the cool part about this relaxed R1CS form is that now when you do the RLC thing as we did before, it turns out, with the right D's and E's, you have the same property that our toy example had, right? Essentially, you can take Z1, Z, or one of these, and we have another one. EZ2. And then you can convert these into some Z3 form. Oh, that's EZ3 dash. Right. So you can convert two of these into one of these. And as long as, the same Z3 is created, the same way, Z1 plus RZ2 kind of thing, where R is like our RLC input, then verifying this third equation is sufficient. So as before, we come to the same kind of setup where if you want to verify n instances of some relationship, this relationship being defined by this A, this B, this C, this D, this E. So for instance, very concrete example could be each of these. So the A, B, C, D, E could represent the addition of Fibonacci, right? It could be like the previous term plus the new term equals the third or whatever the next layer term, right? And this is like very concretely like ABC instance, and we convert this to an ABCDE instance where D and E by default are some I guess some simple combination of these that we won't go into too much detail about, but right. So we create this ABCDE setup, and then yeah, we want to repeat n instances of this. So as before, we can verify some final folded version. And then for each of these, you have the same kind of verification. That for all I up to n.
Hey, Nolan, I have a couple questions.
Yep, for sure.
So my first question is in the randomness of the linear combinations, when you're doing a recursion like this, are you using fresh randomness every time?
Right. So after each iteration, you would have to create a new ZI, which would need a new R.
I see. So it's like RI. It's a different R for every I.
Oh yeah, good point. Yeah.
Okay. And then the second question was like this new relaxed R1CS stuff. We kind of motivated it so that we're like transforming the R1CS constraint so that it's like foldable in this way, kind of. I'm wondering if is that the only advantage of this relaxed R1CS, or does it like if by adding these new terms, is there some like extra expressivity or like ways of representing some constraints in a more efficient way or something like that? Or does it really have no impact on that? And like the extra terms D and E are like fully determined just by the R1CS ABCs. I don't know if that makes sense as a question.
Yeah, that totally makes sense. So
Okay.
if I understand correctly, the question is, can we do something more than just R1CS by this relaxed form, right?
Yeah, or like maybe express constraints even in a more efficient way that we would need. We would have needed, more constraints or something like that.
Right. Yeah, exactly. So I guess the sort of equivalence there is that maybe I should have done like some. So R1CS is actually equal to NP, right? And up to a constant factor, you can convert an R1CS to a relaxed R1CS. So any gains you make would be in constant factors at best. And you can actually see this equivalence of why R1CS and relaxed R1CS are equivalent, right? So you can take any of this, like any R1CS kind of relationship, and just add the D and E terms, right, with 0. And they're equivalent, right? And to convert from a relaxed R1CS back to a normal R1CS, I believe you end up just adding double the constraints. So I think the paper goes into more detail about this, but it's basically like you would at most be saving like 2x, which is, I guess it might be beneficial in some practical applications, but I don't think it's worth the hassle.
I see. I see. Makes sense. All right. Thank you.
Yeah, for
I
sure.
also have a question. Like, yeah,
Mhm.
I think like can be the same for different ZI, right? Because if you use the same R, then the formula of each Z should be a polynomial in terms of R. So it's also okay if I think if we just use the same R, right?
Right. So in theory, you could use the same R, but I guess in practice, like the one detail I'm not going over is that in practice, you do some fiat Shamir thing, right? Where you first commit the like Z terms, right? So you would commit Z1, Z2 up to whatever, and then you sample a R, right? So in case you already know all of your instances, right? Yes, you can already commit to all of the Z instances, sample an R, and then use an R the same one repeatedly. But if you want to do like IVC, I think the formal definition requires that you do not know the next value in the futures, right? So in that case, you would at each step commit the new ZI that you got, right? Spit out an output, convert that, and then keep going forward. Does that sort of make sense?
I guess like because each CI depends on the previous several Z. So I think it's okay if you just commit Z1, Z2, and then use the sample the R, and then all the other things are deterministic.
Right. So in practice, actually, so this Z, I guess one more thing I should have added is that I guess that's part of the next step, but in fact, you can plug in more than so there is some ZI that's going from ZI to ZI plus one, but also at each step you can plug in some private witness, which would
Okay,
make
got
this
you.
ZI plus one indeterminable.
Got you. Yeah.
Does that make sense?
Yeah, makes sense. Like I think you are like you want to say that we can use the different RI for Nova, right? Yeah.
Yes.
And in
Yeah.
practice, we might use the same R. Okay, thank you.
Right. Yeah. So I guess the main point is that so you could have some private witness, which would make the future ZIs indeterminable. Right. And yeah, I guess I'm skipping over a lot of things. So the key part is that the future ZIs are supposed to be indeterminable because of how we define IVC. And therefore you would in theory at least to do this cleanly, you would always commit R at or sample R at each step. But yes, in practice, if you already know like all the ZIs, then yes, you can do it. You sample
Okay,
R once.
great, totally got you. Thank you.
Cool. Yep. Oh yeah, I guess one more thing that I should have talked about a little bit was folding schemes. So right. So I guess so far at this step, we have some version of R1CS, relaxed R1CS, which we can do this folding thing on. And I guess we haven't really defined what folding is, but essentially you can take two instances of the same type of problem. So you can imagine this is like some ZK EVM like step, right? Or one gas unit or something of that sort. And convert that into one instance that we want to verify, as well as some overhead that we incur to verify that the sort of cascading was correctly done. So what can we? So what is, I guess, the general structure of the thing that we have created? That is, I guess, the sort of thing I was starting to get at here, which is folding schemes. So essentially, we have right. So we essentially have some input, let's say Z1, right? We have some output Z2. We could have some private witness. Right. And then this is some R1CS. So for instance, this could be let's say VM step, right? So this is one step of some circuit or some actual relationship that we want to verify. And then how is I guess the output Z2 to this created? We also need to verify that this RI step was done correctly, right? So to do that, we also have some small box here, and I'll just label this box some check of this sort, right? Z or this is say Z2 is equal to order term Z1 plus Z0 or something. Something of this sort, right? So we have two checks. One is like the original like thing that we want to repeat, as well as some small overhead, right? And I think generally in this is like the recursion threshold is sort of the way to think about this. And in case of Nova, it turns out this is equivalent to adding about 10,000 gates or something to your circuit. So that means just for the overhead of 10,000 gates, you are able to do n instances of the same problem instead of one instance for the same verifier cost. That is right. So what are you able to achieve here? You're able to take some input Z1. You're able to give some private witness. You're able to check some relationship, which is some R1CS VM step. Right. You're able to check that the folding was done correctly. So let's call this folding subcircuit or something. Right. So you have some small piece, and then you get some output Z2. Right. So now you can take this output Z2 and you can repeat this whole thing. Right. You plug it into step 2. Right. Same way, you have some private witness. And then same way you have some Z3 output, right? You keep on repeating this, and essentially you can do as many steps as you want, right? So what was the overhead of doing this? Or I guess like what is even the output, right? So as output, you get whatever relationship is in this VM step, right? This relationship is expressed like some A dot Z times B dot Z equals C dot Z plus D dot Z plus D dot Z, whatever, right? Whatever this equation is, right? And then you have some value of Z that you output, right, after n steps or whatever, right? And then the only overhead you incurred was that actually in reality you had to pad all of these A dot Z, B dot Z, all of these terms with the folding subcircuit, right? So your original was this, let's say, and then you convert it to this A dash B dash C dash stuff. And each of these is like you only added as many gates as the folding plus original. So this is pretty nice. And I guess like one more sort of I guess like for a programmer, like the input looks like you have some public input, which in this case is Z1, Z2, Z stuff, right? Some pub in, let's say, some pub out at each step. And you're able to route this pub output, R1CS, through many iterations of this R1CS. So for instance, this could be, I have some ZK EVM code, and then I have some program counter in that ZK EVM code. And at each step, I iterate the program counter by 1, execute my step circuit or verify like whatever relationship my step circuit is supposed to verify. And at each step, I'm able to get some private witness. So this could be, I'm verifying, the Ketchak pre-image of some value or something of this sort, right? And ultimately, at the end, what you get is like, you get just like one R1CS and one value of Z. And the cool part is, we never left like R1CS to do all of this, right? And in case of SNARK or something, you would have to compile down to Fry, and then re-verify that Fry instance and another SNARK, or do all of that stuff. And in this case, we never left this IOP land, so to say. And we have just this value of Z that was created using like the RLC trick. And in reality, we also want Z to have ZK, right? So the sort of typical trick to do like both of these properties is the two properties being we need linearly homomorphic stuff and we need ZK. And the coolest primitive to do that is Pedersen commitments. So the Z is actually a Pedersen commitment. Right. And Pedersen, the cool part about Pedersen commitments is that the only thing you require to do Pedersen commitments is like some group that has discrete log hardness. You do not need, pairing functions or for instance, like Grad 16, you need pairing functions, KZG, you need pairing functions, or any of these other primitives. You need all of this heavy machinery of cryptography. And in this case, we just needed pretty simple Pedersen commitments. And we have, this folding scheme, which is able to take n instances of a problem and convert it into one with some overhead, right? Folding scheme, and the key cool properties of this folding scheme is that it only needs D-log hardness. It only needs D-log hardness. It's able to, so the recursion threshold, which is the overhead, is just 10,000 gates. And those 10,000 gates are checking, that the RLC trick was done correctly. Recursion threshold is 10,000 gates or something to that order. I guess maybe I should take a pause here, and if anyone has any questions or anything, before we start diving into like, I guess, why this is very cool and what are the cool applications of having this set up.
Yeah, so I have a question on the like recursive diagram. If you scroll up a bit. Oh, yeah, the one in the top left where we have like Z1 fed into the R1CS VM step and then some like overhead and Z2. So like the way we drew it, the threshold part is saying that Z2 is equal to R times Z1 plus Z0. But then like what does Z2 have to do with the VM step? Like where, like I guess where is Z0 coming from, and shouldn't Z2 be in terms of like the private witness and somehow the VM step?
Right. So in this case, yeah, I guess I abstracted away a lot of things, but the Z0 is actually like in this case, let's just say. So you would have some, I guess actually another thing to note is that the Z is actually some hash of your public input as well as your private witness. So when you do this RLC, you're actually verifying that the private witness was also formed correctly, or the private witness was inputted correctly into your next iteration. So I guess let's imagine, this was like some better. Oops. Let's say this was like some ZI, right? So you would verify this R times ZI minus 1 plus, so the ZI minus 1 would contain, some hash of all the I minus 1th, up to I minus 1th stuff. And then at this step, you would add in some WI, comma, PI hash. Does that make more sense?
Yeah, and so like the WI stuff is what's happening kind of with the private witness at this particular step. So like you're mixing like the previous kind of state with the current step that you're doing to get the output of your current step.
Yes, exactly. So essentially the like the RLC is sampling over the previous distribution or like the previous input, as well as whatever new state change you have made.
Good. Okay. That makes more sense. Thanks. Yeah.
Sure. anything else? Anything else? Okay, cool. Yeah, in that case, right. Wait, I actually think I had a note somewhere about all the cool properties. Let me just go through this and add this one. Oh yeah, here. Right, we went through the DOI relationship, we went through the R1CS setup. Right. Okay. So just to reiterate, we have this folding scheme now, which only needs D-log hardness, and recursion threshold is pretty low, and only 10,000 gates. So what are the cool things we can do with this? So the first cool thing that I think a lot of people might find interesting. Let me see if this works actually. So one of the efforts that have been recently ongoing is, let's see, /circum. So one of the efforts that has been ongoing in the recent past has been this effort to take a lot of signature schemes and put them in ZK, just because you get a lot of cool identity primitives and those kinds of things. So one of those has been circom ECDSA. And the hard part about doing these in most proving systems is that to do an EC operation is in a 256-bit field. And Ethereum or EVM the pre-compiles are for BN254, which is a 254-bit field. So you end up having to do a lot of big-int arithmetic to be able to do the 256-bit field operations. But the cool part about Nova is that Nova only needs D-log hardness. Oh, I guess the reason you need to use BN254 in that case is that the proving schemes we use is like Grad16 or Planck, and both of them need the pairing, or Planck with KZG, and both of those need the pairing function. And BN254 is an EC cycle which does have pairing function. But in this case with Nova, we have created a folding scheme for R1CS, which only needs discrete log hardness. And SecP256, which is the ECDSA field, does have discrete log hardness. So if you could create some R1CS VM, essentially, right, where let's say your operators are like some simple, I don't know, like some MIPS machine or something, right? And then additionally you have some EC add, EC mul, and all of those operators, right? You would have some R1CS, which you can use to do an ECDSA verification or a signature verification within just this Nova VM. And then you as an output get some R1CS instance in SecP256K1, which you can then verify on chain or in another Grad16 or Planck proof. But then at that step, you do need some big end. Right. So the cool part we got here is that just because we only need discrete log hardness, we get much more compatibility with a lot of different crypto primitives, which includes ECDSA, which happens to be a very useful one. Right. Oh, I guess one thing I did not note is that so you do need an EC curve cycle. Which is to say, so when we were doing, all of these folding things, one detail that I sort of glossed over is that actually these are happening over a cycle. So in case of an EC cycle, the base field is the scalar field of the other one. So any operation here translates to some operation with the points in the other curve. And you needed it to do like this folding verification step. Oh yeah, I guess ECDSA or SecP does happen to have a cycle with the SecQ curve, which is why that sort of works. Right. So that is, I guess, one cool property. Other cool properties, right? Yeah. So I guess in general, in terms of application stuff, VMs are basically, I think, the ideal example of the kinds of things. So for instance, ML, you do a lot of let's say decision trees or something, right? You do a lot of low depth, or in each instance, you're not doing that much compute, but you just have lots of many random forest trees or something, right? So ML is a good target. Oh, I see there's is EC cycle required or a nice to have? Yes, so EC cycle is required. And I won't go into too much detail why, but the paper goes into like how the Pedersen commitments are actually instantiated, and I think that will make it a lot clearer why they're required. Right. Yeah, so you have VMs, which are generally like the coolest application of this. So ML is one good setup where you can create essentially a VM. And I guess basically the way I have been thinking about this is like you think of some like small VM that is pretty ubiquitous, right? And then you add essentially like pre-compiles to this VM, right? So in case of ECDSA, you would add, the ECAD, ECMOL pre-compiles, right? And for each pre-compile you add, you pay the cost in one instance, right? So the R1CS or the relaxed R1CS would look slightly larger. But the advantage you get is that to do n iterations of this VM, it's the same cost to the verifier. Right. So ML is a good one, ECDSA and things of that sort are a good one. And then of course, ZK EVMs are a good example. ZK EVMs or just ZK VMs in general. And then I think I had more examples. Oh yeah, VDFs. Right. So one ongoing effort that's worth mentioning is that EF and Filecoin are working on building VDFs using Nova. And in the case of VDF, essentially what's happening is that a VDF to do over n time is basically just n iterations of some function, or in practice this function ends up being like take the fifth root of something and verify that the fifth root, right? And to do one iteration, you just need to verify this one equation. So you can do n iterations of this in Nova and get some output that's like only equivalent to verifying one step of the VDF computationally. Right, so VDFs are a good one. Another good one is LIRC language. So LIRC language is something I believe Filecoin or folks related to Filecoin are working on. And with LIRC language, the idea is that they have created a Lisp dialect, and they have some very small Lisp VM. And this Lisp VM, they write in Nova, and then as the output, you still get some constant size, or not constant, but fixed size output to verify, right? So I guess just to reiterate, what we got as our ability was, we were able to take n steps of m constraints, let's say, and I'm losing the word constraints, using the word constraints pretty loosely, and we were able to take Nova, supply whatever our inputs were, n, let's say n inputs, simplicity, and then as an output we got something of m constraints to verify. Right, so I'll just underline these variables. Right, so if let's say you were actually running this on some I don't know, low compute environment like EVM or on blockchains or something, these m constraints might still be a lot to verify, right? Because for instance, with some ECAD and ECMOL, this is still pretty heavy. So one thing you can do, which circles back to the sort of analogy with SNARKs in SNARKs, you can take these m constraints and then verify them in an actual SNARK. So finally, you take whatever output Nova gives you, and then you verify that output R1CS in Rod 16/Blanc or whatever it is, right? And you get the property that now this is order 1 output or order 1 cost to verify. And we started with n steps of m constraints. Nova gave us the fast prover properties, and whatever final SNARK we use gave us like the fast verifier properties. So this circles back to the approach with Starks and SNARKs. We had fast prover, and now we have fast verifier. Yeah, let's see. Is there anything else worth mentioning? Oh yeah. So I guess now, wait, can I split the screen? Oh, yeah. I go here, and I should have opened these tabs before, but yeah. So I guess this is the Nova repository. Because this idea is so clean, it's also worth mentioning that the code is pretty small. I believe this is like 2,000-3,000 lines of code, and it's like pretty I think nice to audit and just like very clean theoretically. So I think that's very nice compared to Starks and stuff, which I personally am not a big fan of the security proofs and stuff of. And then another cool thing worth mentioning is that oh yeah, I guess one thing I sort of glossed over is that to do this, we were only using MSMs. So the only operation you need to do is like r times some vector is equal to some plus some vector is equal to some third vector, right? So you only needed MSMs. And the cool part about MSMs is that you can accelerate these much more nicely than FFTs or something on hardware. And the Nova repo actually uses this library called Pasta MSM, I believe. Yeah, Pasta MSM from supranational, which already does hardware acceleration and all of those things. So I believe if you have some application and you just plug it on a GPU setup, your application should be really, really fast with Nova. Right. So I guess those were those things. And then another cool thing that Nova gets here is because we were only working with R1CS, CIRCOM and other ecosystem that developed around like Quad 16 stuff is highly compatible with R1CS and therefore Nova. And so for instance, recently I did this effort to make Nova Scotia, which can take any CIRCOM circuit that you have and just use it as the step circuit in your Nova setup. And let's see. I mean, the repo is online, but as an example, what this actually looks like is, for instance, I have this Bitcoin circuit, which is verifying that one Bitcoin block is formed correctly. So here, I have whatever my check one block function. And let's see. So my main takes in as input some steps, some step input, right? This is my, I guess essentially my public input, right? And then I spit out the same amount of public output, right? Which will then get piped further and further. So what is my output and input here? So I take in, previous block hash as my input, and spit out, current block hash or whatever. And at each step, I give it Bitcoin headers or block headers, let's say block headers. And my step circuit will verify. Oh yeah, so you can see that this inputs the block headers as the private witness, and then you can verify that at each step that this block hash has enough proof of work and all the difficulty and all of that stuff matches up. So essentially, you're able to verify that one iteration or one block was formed correctly. And then if you repeat this enough times, you're able to verify a chain of blocks was verified correctly. And you only needed the computational cost of verifying one of these blocks. So I have some benchmarks also. Let's see. Oh, yeah. So on my laptop, which is some pretty old, pretty mediocre hardware. It turns out to verify, hundreds of, or how many blocks are, oh yeah, 120 blocks. It takes, about a minute to prove, and the verification is, fixed cost 200 milliseconds or something as the output. And of course, if you have good GPU, good hardware, all of that stuff, this will be much faster. Right. Yeah, and I mean, this repo, has some toy examples and all of that kind of stuff. And oh yeah, I also have this diagram here, which should reiterate on the hand-drawn. Wow, this hand-drawn one is not that neat, but so this repo diagram should be much clearer. Yeah. Cool. Yeah, I guess how are we doing on time and stuff? Is there any constraints?
Yeah, we can do questions now, or if there's any other topic you want to talk about, we have some time.
Oh, sure. Yeah, I guess just to quickly mention some of the ongoing stuff that would be, if any of the people in this call are interested in working on Nova. I guess like some of the things that people already are working on is like things like writing a verifier for relaxed RNCS in Grad 16 and Plonk. I guess another note I should make is the original Nova repo has a I guess converter of relaxed RNCS into a Spartan scheme. Which Spartan is another scheme which also works with RNCS. It is also made by the same people and based on like IPA. But not to go into too much detail, essentially, you can replace this Spartan with any, or this Spartan steps in at this step. So you can replace this with any Grad 16, Plonk, or whatever else. And then you can verify that on EVM or wherever, right? So one of the efforts that's ongoing is writing some verifiers in common, like Circom or Hill2 or something of that sort. And then yeah, another effort is to port over. So the current repos are on the pasta curves, from the pasta curves being the ones that Hills2 and Zcash and everyone uses. And one effort is to port them over to the SecQ cycle, so you can then do the fast ECDSA stuff. And then another effort, oh yeah, then there are some folks I know about who are working on VDFs, and then another group of folks working on putting some ZKML models in it. So if any of those things interest you, just like I guess text me or something afterwards, and I can help you connect to the right people or something. Cool. Yeah, I guess besides that, if there's any questions or anything, take.
Awesome. Yeah. Does anyone have any questions? All right. Then we can end it there. Thanks a lot, Nalin. That was really great presentation. I like the whiteboard style. It was good for understanding. So
Yeah, for sure. Thank you.
Yeah, thanks a lot. All right. See you, everybody. Have a great weekend. Bye-bye.
Thank you.